My name is Naveen Ahmed. I am from Department of Electrical and Electronics, PSIT, Bangalore, India. And I will be presenting my paper named as a complete interface device. Communication defines the way we interact. It has made a lot of progress these days. The way we humans communicate is more realistic compared to the way the computers communicate, the way the mechanical systems communicate. I can't speak to my computer the way I speak to my friend. This defines that there exists a communication gap between you or maybe hers and the computers and the processor and the mechanical systems. So the idea was to bridge this gap. The idea was to fill this gap. So the only way was to interface human brain, computer processor and the mechanical systems. Well, when I say interfacing human brain with the processor, it's not an easy task actually, it's very difficult because we'll be handling human brain and the processor, the systems. Well, that was the main idea and goal of the paper actually. Interfacing human brain and processor, what exactly it means. Let me give some example so that you can understand what exactly I'm trying to present here. Say if you close your eyes and all of a sudden a Google homepage or a Baidu homepage appears in front of your eyes, and a virtual keyboard appears in front of your eyes. You can type, say, ICSEM 2011 virtually in front of your eyes and access to it, and you start browsing. All appears in front of your eyes virtually. You can see it, but no one else can see it because it's completely privatized and it is completely virtual in front of your eyes. That was the concept of virtual vision, and this virtual vision gives the concept of virtual world. Let me give another example. How about bringing my parents who are there in India right now in front of me, right here now, now itself? Or how about having a panoramic view of White House in Washington DC all around me, virtually? The idea was to link processor and the brain so that it can send the data from the processor to the brain and induce signals in the brain. The idea was actually, the truth behind is, we actually see the world not through our eyes, but through our brain. So how about bypassing the signals from the optical nerves directly to the brain using a computer? Well, it's not an easy task, so I will suggest a method how it can be done. The same idea can be implemented so that we can give a virtual sensing for the blind people, so that we can make the blind people see the world the way we see. So that was the idea behind it, where you can see that the complete interface device and composes of the brain interface, digital interface and the mechanical interface systems. All these systems will be cascaded together to form the complete interface device. Let's take the brain interface device. Here you can see that the processor is feeding the data to the brain as well as getting part from the brain. So there's a two-way flow of the data between those two things. Human brain specifications. Well, whenever we speak about the human brain, we do realize it's the most complicated creation of the world. So even no matter how precise our readings are, implementing something on human brain is very risky and very tedious job also. So we need to confine ourselves to certain boundaries. So these are my boundaries actually. Say you can take the weight or the dimensions, or there's a frequency range you can classify it as alpha, beta, theta and delta waves. So these are the wave frequency range. We need to confine ourselves. We should not cross this limitation because we need not to burn the neurons of the brain. It is very dangerous also. So as I the diameter of the neuron and resting potential, the potential developed across the two neurons with the variation of ionic concentrations. It is about to be minus 70 millivolts. It's not a precise value, but it keeps varying as per the data. And the neuron conduction velocity. Well, whenever I say velocity, we need to sync two systems. Like the rate at which the processors communicate may be different from the way the neurons communicate. So we need to sync those two systems. That's why we need neuron conduction velocity, an important parameter also. But for me, the important parameter is the magnetic flux across the neuron. Well, whenever a signal flows through a neuron, what is the field intensity developed across it? And it's said to be up to 9 to 48 Gauss. So if I want to implement a signal to the neuron, I need to confine to this range. You should not cross this range because, as I told you, we need to confine to this boundaries itself. Well, I have not taken many of the parameters here. Just for the demonstration's sake, I just took 7 parameters. Still, there are many other parameters we need to consider there. Well, transcranial magnetic stimulation. The definition is extracted from Wikipedia. It says it's a non-invasive method to cause the depolarization in the neurons of the brain. It uses the electromagnetic induction to induce weak electric currents using a rapidly changing magnetic field. The idea was to take a wire assembly which can by varying the currents of the wire network assembly, we can induce the signals to the neurons. The principal electromagnetic induction, that is d phi by dt is equals to E, reduced to Michael Faraday. Well, that idea was taken to induce signals to the brain. So how exactly to induce signal to the brain? That is defined by the algorithm that is installed and coded in the computer program. That can be varied across it and can induce in the neuron. That was the idea, a key idea behind this the project actually. Well, you can see that the transcranial stimulation is already do exist in the medical fields. It's used to stimulate the signals in the medical field actually. The brainwave frequencies. How exactly the brainwave frequencies vary? Here you can see that it has been categorized like whenever a person is sleeping or awake watching TV or any other his activities. Based on that, the brain produces a frequency of waves here. Say, suppose if I see a red color, how do my brain react to it? And I should mention that each brain is unique. So for a given excitation, the response may be different from person to person. So that's why we need to create we need to privatize with certain data for the given person. So here you can see that the frequencies are so random here. So it's mathematically expressing it, it would be difficult for us. Maybe there's a fundamental frequency, the constant, the sine and percentile, and it goes on maybe a Fourier series of frequency domain. Whatever. Representing this using the mathematically would be quite difficult. So we need an algorithm to extract as soon as it gets the data from the brain. So based on that, it can analyze and feed the data back to the brain. That was thing. This was the sample wire assembly which I designed actually. Well, here you can see that the horizontal and the vertical combination of the wires that I use, I have named it as I1, I2, I3 just for the representation purpose, and I have confined to a particular region because we need not to cross the limitation of the brain. Like this, if this is a vision part of the brain, we should not cross above it. So designing is mathematically a bit complex. And analyzing this is actually well, you need to be very sound in electromagnetics. Even simple equations like B is equal to mu naught by 4 pi into n by I into I integral over d phi will be visualizing it will be difficult. So like you need a computer something like a MATLAB or something like that to analyze it. These were some of my previous attempts to trap the signals, but I failed because of the external noise induced there. I couldn't extract the basic signal from the noise portion. That was the thing actually. Test mode and digital interface devices. Well, as I told you earlier, creating a database is an important thing here because as I told you, each brain is unique. So for a given data, we ask a person to see red color for example, and we take the feedback and we ask him to see the blue and green and many objects. So based on that data will be stored in the database for his reference, and that database analyzes as per the algorithm and feeds data back to the brain. And signals from the database. Well, once we get a database, we need to direct the signals to the addressing modules. And each addressing module will be associated with a unique wire there. So each wire carries a different current as per the algorithm of the program. And that current varies with reference to time, and hence we induce signal the thing. So we suppose if we have thousands of wires, we can have millions of combinations in the magnetic field intensity, and those millions of combinations can address millions of neurons in a given confined region. So do the thing and cascading the different digital interface device to the system. Well, this idea actually, like you need to cascade it because see, suppose if I want to control my AC and all of a sudden a knob appears in front of my eyes and I can control it. How about that idea? How about controlling the mechanical systems around you? Like you can control mechanically open the door and close the door virtually in front of your eyes. That was the idea of cascading different digital interface systems to this system. Well, this part is very easily, any high school student can do that because we already have advanced technology, automated doors, automated cars, everything is automated these days. So that was the idea. This is just a sample demonstration. Like you can, I will explain how exactly I approach this problem. Here actually I am transmitting the signals like the digital signals like ones and zeros to the transmitter there. Well, the LED represents high and low is the input to it. So the system is made as wireless here. So actually the incomplete part here is the brain interface systems. So I'm mechanically feeding the data to the computer. So I'm feeding high, I'm feeding low there. So based on this data is fed to the computer database. Well, here you can see that ones and zeros are taken into this database there. So if I have two, like 1 and 0, 2 square, 4, so I can have 4 combinations. interface systems. How about controlling the music systems there? This is the algorithm. We're controlling the music systems there, and controlling the motors, which will be coming up next. And also we didn't want it to consume, actually we wanted to make it as a consumer oriented. So the person who is using should not be confined to certain boundaries. We wanted it to be very free. We wanted him to use the maybe the appliances present in the first floor, sitting in the ground floor. So we also thought of making it as a long range interfacing. So we'll show how long it was able to link actually. Here you can see actually I'm controlling those digital impulses from my room, and I'm walking towards my friend's room there in the hostel. The idea was actually I'm approaching this project actually from my field. That is my electrical and electronics. I'm approaching from that field. I'm not a neuroscientist or even a biology student to analyze the brain. So it was a bit difficult for me to understand how complex the brain was actually. Even many neuroscientists are working all over the world to understand how complex the brain works. Exactly works. So this is actually long range interfacing, where you can control many small DC motors. Or just for the demonstration purpose, I will use this video. Where you can make some advanced technologies from using this, implementing this idea also. Mechanical interfacing. After cascading all the systems, we get mechanical interfacing systems. Like cascading mechanical interfacing systems, you can control the mechanical objects around you. Or like due to some action in the virtual world around my eyes, I can control the mechanical system in the real world. Some action in the virtual world results an action in the real world. So that was the thing. And coupling the brain and digital interface systems and mechanical interfaces yields to a complete interface device, where everything is realistic in the interfacing systems. And thus we can obtain a complete interface device. This is a block diagram. Here you can see the human